Now on to section 1.2, the graph of a function. Probably this should be called Introduction to the Graph of a Function. We'll spend the next 2-3 sections in this chapter elaborating on graphings of functions. In this section, we identify the graph of a function and obtain information from or about the graph of a function. So nothing in great detail in this section, but details to follow in the upcoming sections. When a function is defined by an equation in x and y, the graph of the function is a set of points, x comma y, in the xy plane, in the Cartesian plane, that satisfy the equation. So every point on the graph is associated with the value of the function, and every value of the function is associated with a point on the graph of the function. So that's how the algebraic equation stuff interacts with the geometric pictorial graph stuff. By the definition of function, there's only one y corresponding to a given x. And we've mentioned this previously in the very definition of function. Each x value is associated, each x value in the domain is associated with exactly one y value in the range. And this leads us to the geometric idea of the vertical line test. I'll state it as a theorem. A set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. Probably you're familiar with the vertical line test. Yeah, there's a horizontal line test that tests for something else related to functions as well. But for us, one input has at most exactly one good input has exactly one output when dealing with a function. That justifies the fact that graphically, vertical lines intersect graphs in at most one point. So either not at all, in which case you haven't chosen an x value that represents that vertical line. You haven't chosen an x value in the domain, so there were no points on the curve. And in the event that you do choose an x value from the domain, then there'll be exactly one y value associated with it, that y value lying in the range. So that's why the at most one. Let's look at a couple of examples. So we'll start this graphical adventure where they give us the graph. Well, they give us that thing there, and we're supposed to extract a bunch of information from that. I complained a little bit about this. It's not clear what's going on with this graph. I think I know what they're suggesting. I definitely know what they're suggesting, but it might be a little bit of a puzzle to you. They've given us this graph and they ask us, is it a function? What, it continues on in this direction? Does it have a horizontal asymptote or something? Or does it continue to grow in this direction? What's happening over here? Does it go down below the x-axis? Their implication is, and granted, this is not spelled out well at this stage, their implication is that on the left-hand side, this is getting, we'll discuss this in a good deal more detail later. The graph is getting, as we move to the left, closer and closer to the x-axis, but it never gets there. That's one of the conditions that implies a horizontal asymptote. And on the right-hand side, they mean this graph gets steeper and steeper, but I can continue to plug x values larger and larger in. They mean this, if you've been exposed to this before, I think they mean this to be the graph of some exponential function. Trust me, what you're going to do. This is not a lot of information, but what they ask us is the following. Determine whether the graph is that of a function by using the vertical line test. If it is, use the graph to find the domain and range, the intercepts, if any symmetry with respect to x-axis, y-axis, and origin. Okay, well, is it a function? Does it pass the vertical line test? A vertical line will intersect the graph in exactly one point, assuming it's extended according to the pattern we see. That is, it continues off without bound in the left direction. I mean, that's what they're implying by the arrow here. And it continues off in the right direction That's what the arrow means here. And I can plug in numbers very far to the right, and we may get out really big output values, but you can plug in any real number as their implication. On this side, you'll get out small positive numbers, and on this side, you'll get out really big positive numbers. But it doesn't double back or anything like that. We have to read that into this little bit of information here. With that understood, then yeah, vertical line will only intersect a thing in at most one point. In fact, exactly one point they imply from the picture. So it is a function by the vertical line test. Now, about the domain and range, you got to take my little added bit of information into account on that. The domain is all possible x values, I say, assuming the graph extends according to the pattern we see, that extends onward without bound to the left and extends onward without bound to the right. And I can plug in all x values and produce associated y values. If you believe that from this little piece of information and my added conversation, then the domain is all real numbers. I can plug in any value for x and there will be a corresponding y value. In fact, this is related to the way we describe the vertical line test. Every vertical line will intersect the graph in exactly one point. Domain, range. Ranges are hard to find in general. If you have a graph of the function, then it's not so hard to find the range. But graphing functions is hard too. So, and we don't have much equipment so far, but they've given us a graph. So with the previous conversation on the table, what y values do you get out? The range is all possible y values for where the function is defined, that is for good input values, the set of y values for which there's a point xf of x or xy on the graph. So I'm looking at the y-axis here. Can you get out y equals 0? Nah, they don't intend that to be the case. No. You never get y equals 0 out. Remember, in the left-hand direction, this gets closer and closer to the x-axis, but never gets there. Details to follow on that kind of verbiage. So it never takes on the value 0. It never takes on any of these negative values down here. There's nothing drawn. There's no points on the x-axis. It doesn't take the value 0. There's nothing drawn in the third and fourth quadrant. So it never takes on any of these negative y values. And it looks like it's going to take on anything greater than 0. If it's just a little bit greater than 0, it takes on that value somewhere over here far to the left. And it takes on all positive y values given this trend of going upward. So what's the domain? I'm sorry, what's the range? All positive real numbers. We don't get 0 out. We don't get anything negative out, assuming it follows this pattern. And we get everything greater than 0 out. That is, the range is all x such that x is greater than 0, or the interval, in interval notation, the interval 0 to infinity. And I describe this in terms of looking at horizontal lines. Right? We're trying to see, does this take on the value y equals b? Well, what I do, if I wanted to see if it takes on the value -3, I'd go to y equals -3 and look at that horizontal line. Does this ever intersect the function? It does not. How about +3? No, let's do +2. I'd look back and forth and see if there's any points on the curve where the y value is +2, and it looks like it's right about there. Looks like it's around 1.5, 2. The fact that there is a point on the graph that has a y coordinate of 2 tells you 2 is in the range. And similarly, if I take any horizontal line above the x-axis, it intersects this curve somewhere. And if the trend continues as established in their tiny little graph, then the horizontal line actually intersects this curve in exactly one point as well. Not relevant to the current conversation, though. It's relevant later on when we talk about one-to-one functions and inverses. So that takes care of domain, range. What was next? Symmetries. Oh, intercepts. What about intercepts? I shrunk the image a little bit to get more information on the slide here. Never intersects the x-axis. We don't have y equals 0 as an output. We decided previously 0 is not in the range. How about the y-axis? Does it ever intersect the y-axis? Right there. When x is 0, we get y equals, it looks like 1. So there's no x-intercept. The y-intercept is 1. More appropriately, it's the point 0, 1. We've usually expressed these in terms of ones. Actually, I wish I would have expressed this in terms of the point 0, 1. We've usually expressed these, in terms of points, coordinates of points. I wouldn't be surprised elsewhere you would see the y-intercept is 1. Hey, if you're talking y-intercept, of course, x is 0, but we have commonly expressed those in ordered pair notation. No x-intercept, never crosses the x-axis or touches it. Now for symmetries, yeah. The graph is not symmetric with respect to the x-axis. That was the first one they asked about. If it was symmetric with respect to the x-axis, whatever happens up here, there would be a mirror image of it below. So there'd be something that's shaped kind of like this below the x-axis. There's nothing down here. So it's not symmetric with respect to the x-axis. It doesn't have that kind of symmetry because there's nothing drawn down here. Anything you see in the first quadrant, there would have to be a mirror image of it in the fourth quadrant. Anything in the second quadrant, there would have to be a mirror image of it in the third quadrant, and there's none of that. Not symmetric with respect to the x-axis. How about the y-axis? Here, we talked about it in terms of folding the paper. Whatever I see happening over here in the first quadrant, we would have to have a mirror image of that happening over here in the second quadrant. And there's nothing over here corresponding to these points in the second quadrant. Over here in the second quadrant, we've got these points that get close to the x-axis. If it were symmetric with respect to the y-axis, we'd have to have a corresponding picture over here, and there's nothing corresponding to these points. So this is not a mirror image of itself with respect to the y-axis, and it's not symmetric with respect to the y-axis. How about the origin? In the origin, we had illustrated it with a winking smiley face. We go over and up and find a point on the graph. And if we had symmetry with respect to the origin, we'd go back and down the same amount and find a corresponding point. What that means is whatever happens up here in the first quadrant, there should be some kind of mirror image of that down here in the third quadrant. And there's nothing in the third quadrant, so it doesn't have that kind of symmetry. Also, whatever happens here in the second quadrant, there would have to be corresponding behavior down here in the fourth quadrant, and there's nothing in the fourth quadrant. So it doesn't have symmetry with respect to the origin either. So it has none of those symmetries. Whoops. And that's everything they ask us about this one. Having given us the graph, let's look at another one where they also give us the graph and ask us, is it a function? And they ask about the symmetries, if it is a function. So number 18 says, determine whether the graph is that of a function by using the vertical line test. If it is, then check out all this symmetry stuff. Well, it isn't. So if we strictly read this question, it says if it is a function, then talk about domains and intercepts and all that stuff. Well, it's not a function. You can find a vertical line that intersects the graph of this in more than one point. Take the vertical line x equals 0. X equals 0, that's the y-axis. It intersects at this point and this point, the point 0, 2, and the point 0, negative 2. 0, 2, 0, negative 2. This is mislabeled here, typo. I will get that corrected. But it intersects in more than one point. 0, negative 2, sorry, and 0, positive 2 is where the intersections are with the y-axis. Violates the vertical line test. It's not a function. Okay, if it is a function, then blah, blah, blah. So I didn't write that out because that's not our problem, but let's discuss it anyhow. What's the domain and range? What are the possible x values? Well, we get the x values ranging from negative 2 to 2. And there's points on the curve that correspond to any x value between negative 2 and 2, including the endpoints. I'd say the domain of this relation is negative 2 to 2, square brackets, the closed interval from negative 2 to 2. Range, is y ranges from -2 to 2. Every y value between -2 and 2, there's a point on the curve. In fact, there's two of them. So I would call the range of the relationship that determines this. It's a circle, and we've dealt with the equations of circles already. But the y values will range from -2 to 2. Intercepts, 2, 0, -2, 0 are the x-intercepts. Y-intercepts, 0, 2, 0, -2. Symmetries. Well, this is a good one actually to illustrate symmetries. It's got all this symmetry stuff. Is it symmetric with respect to the x-axis? Yeah. Take it and fold it about the x-axis, or flip the plane over with respect to the x-axis, take a mirror image. Everything that happens up here, there's a corresponding behavior down here, and vice versa. Symmetry with respect to the y-axis. Yeah, everything that happens over here, there's corresponding points over here. We described it in terms of replacing x with -x algebraically, but graphically, I think in terms of mirror images. How about symmetry with respect to the origin? Let's see, we'd look at maybe what happens, how about what happens in the first quadrant? We get this little piece here. There should be corresponding points in the third quadrant, corresponding to the arc in this order, starting at the x-axis and moving up, are these points, starting at the x-axis and moving down. It has that kind of symmetry, at least between the first and third quadrants. If I look up here, and say start along the y-axis and move down in the second quadrant, we'd see the same mirror image kind of behavior, starting at the y-axis and moving up down here. Here we've got positive y-axis and moving down. Here we've got negative y-axis and moving up. That positive, negative, up, down thing is the way that we tested for symmetry with respect to the origin. So this actually has all three of those symmetries. It's a circle. It's really, really symmetric. It's got more symmetries than that, it turns out, but these are the only ones we're interested in. So there's how to take a graph and determine domains and ranges and intercepts and symmetries. We're more interested in creating graphs, at least in chapter 2, that's the ultimate goal. Here they've given us graphs, and there's how graphs can be used to determine those things. Another little statement. If xy is a point on the graph of function f, then y is the value of f at x, that is y equals f of x. So I stated this verbally earlier, but that's how you relate the geometry of the graph to the algebra of the equations. And conversely, if y equals f of x, then xy is a point on the graph. So all a graph of a function is I call it a geometric way to interpret the algebra of a function expressed in terms of an equation. You graph functions. We'll spend a fair amount of time graphing functions in chapter 2. You'll spend a fair amount of time in calculus 1 graphing functions. Can you graph equations that aren't functions? In some special cases, circles. Circles are determined by equations. We had standard form of a circle and all that stuff a few sections back. And those are not functions for the same reason that example we just looked at wasn't a function. It was a circle. It violates the vertical line test. So usually you graph functions, but there's some equations you can graph, equations resulting in graphs that violate the vertical line test. Those are usually harder to deal with, and you'll only see them in special cases, like circles, maybe some conic sections is what you'll deal with in precalculus. Precalculus 2, you'll deal with conic sections in general. And let's just do a handful more examples. Like I said, the bulk of the details on graphing are contained in the following sections. Number 26 says, consider f of x equals -3x squared plus 5x. Is the point -1, 2 on the graph of f? Well, we'll plug in -1 and see if we get 2 out. If so, yes. If not, nope. If x equals -2, what's f of x? So we'll plug -2 into the function. Based on this information, what points on the graph of the function? If f of x equals -2, what is x? Here they gave us x and ask us what is y, basically. And here they've given us y and asked us what is x. And based on that information, what's it tell you about points on the graph? What's the domain of a function? We're pretty good at finding domains already. List the x-intercepts, the y-intercepts, and they didn't ask us to graph it. We don't have a clever way of graphing this. Not yet. We could plot a whole bunch of points and hope for the best. We'll have a clever way of dealing with this in chapter 2. First question, is the point -1, 2 on the graph of the function? Well, let's take x equals -1, plug it into the function. F of x, that is f of -1 equals, go back up here, wherever you see an x, replace it with a -1. So we get -3 times -1 squared plus 5 times -1. I say it quickly, verbally trying to deal with this parentheses stuff. You get -3 times -1 squared. Don't forget the parentheses. The squaring absorbs that negative sign, giving you -3 times +1. The negative out here carries over. The negative in there disappeared. One negative yielding the -3. 5 times -1 is -5. So we get that, we get -8. So when we plugged in -1, we got out -8. That tells you the point -1, -8 is on the graph, but not the point -1, 2. That's not on the graph. When you plug in -1, you get out -8. You don't get out 2. That point's on the graph, not that one, not the -1, 2. No, not on the graph. To find points, we can plug in numbers. To get an idea of the graph in general, plugging in numbers is not a good idea if you just do it arbitrarily. If you do it in an educated way, then that's the way to go. Plotting points, and they're special points, and you know why they're special. Part B, if x equals -2, what's f of x? Okay, same idea. We'll plug -2 into the function. That'll give us -3 times -2 squared plus 5 times -2. The negative is absorbed. We get -3 times 4, -3 times 4. 5 times -2 is -10. That's what? -12 minus 10, -22 is the arithmetic. That's what you get when you plug in -2. Based on this information, what point is on the graph? The input value -2 and the output value -22. -2, -22. That's a point on the graph associated with that x value. Part C, if f of x equals -2, what's x? Okay, this is different. They didn't give you the x value, they gave you the function value. If f of x equals -2, we know f of x is -3x squared plus 5x, definition of the function. Set it equal to -2 and solve this equation. Okay, how about we take everything to the right-hand side? That'll give us a leading coefficient that's positive. Maybe that's helpful. So we'll have positive 3x squared minus 5x minus 2, positive 3x squared minus 5x minus 2. We have 0 on the other side. So I've written it interchanging left and right-hand sides just to make it more familiar looking. So can you factor this? Maybe. An alternate way of dealing with it is use a quadratic equation. That always works. If it's got one solution, that'll tell us. If it's got two real solutions, that'll tell us. If it's got no real solutions, that'll tell us. So the quadratic equation, quite useful that way. Here we've got A is 3, B is -5, and C is -2. Quadratic equation, know the quadratic equation. It's in the review material and the appendices. We have negative b, that's -5, plus or minus b squared minus 4ac, b -5 squared minus 4a is 3, c is -2. Plug those in over 2a. Simplifying, negative, it's a +5. And here we get -5 squared is 25. Minus a negative, this will give us plus 4 times 3 times 2, it's 12 times 2 gives us a 24 there. Denominator yields a 6. 25 and 24 is 49. Square root of 49 is 7. So this simplifies down to 5 plus or minus 7 over 6. So either x equals 5 minus 7, quantity, over 6. 5 minus 7 is -2. That'd be -2 over 6, which simplifies to -1/3. Or in the case that we add 5 plus 7, quantity over 6 is 12 over 6. Yeah, that's just 2. So corresponding to a function value of -2 is an x value of -1/3 and an x value of 2. Is that a problem in terms of this being a function? No, not at all. We have 2 points with the same y value. That's not a problem. Tells you horizontal line is going to intersect this thing in 2 points. If you take the horizontal line y equals -2, it's going to intersect the graph in 2 places. So what? I don't care at this stage whether horizontal lines intersected 1 point, 2 points, a bunch of points, or no points at all. In terms of dealing with functions, I'm worried about vertical lines. Had we plugged in an x value and got out more than one output value, that's a problem. That's a violation of the vertical line test. One x value in, it's from the domain, one y value out. Nobody said anything about the same y value occurring more than once. That can happen. We get the y value, -2, both when x equals -1/3 and when x equals 2. So we get the point -1/3 comma -2, x comma y, and the point 2 comma -2 are both on the graph. So you can have repeated output values. Sometimes I describe an example of a function as, think of it as a temperature as a function of time in a given place. So at any one time, at a given place, you only get one temperature. But you can get the same temperature at different times. So different input values, different times, it can be the same temperature. You get repeated temperatures, but for a given time, you only get one temperature. That's an informal way to think of the behavior of functions. Yeah, so no problem. With different input values, we got the same output value. That's not a problem. And we deduce that that gives us these 2 points on the graph of the function. It's 2 points that have the same y value. Next, what's the domain? Okay, so what can go wrong? Division by 0, square roots and negatives. There is no division and there are no square roots. So all real numbers, no problems. The only thing that can go wrong at this stage is these 2 things. In your mathematical travels, some other stuff could go wrong. If you deal with trig functions, you can't take the tangent of 90 degrees, for example. You can't take logarithms of negatives. So other things can go wrong. But for us, for now, division by 0 and square roots and negatives are the only thing we'll encounter. We'll build on that when we look at log functions in chapter 5. But the only 2 things we're concerned with now, neither are an issue. So the domain is all real numbers. There's the x-intercepts, if any, of the graph of the function. All right, we did this previously. For x-intercepts, you set y equals, excuse me, y equals to 0. Y equals f of x. So you'll set f of x equal to 0, or -3x squared plus 5x equals to 0. X-intercepts set y equal to 0. Y-intercepts set x equal to 0, as we'll do in the next part. Produces this equation. You need to solve for x. You want to use a quadratic equation. It'll work. This one's easier to see how it factors, though. We can factor in x out. Then we get x times the quantity, -3x plus 5. The only way this product can be 0 is if either x is 0 or this linear term, -3x plus 5 is 0. X is 0 when x is 0. -3x plus 5 is 0 when x is what? 5/3? 5/3. So we get 0 and 5/3 as the x-intercepts, or expressed as points, 0, 0. Remember, we got the y coordinate 0, and 5/3, 0. remember we've got the y coordinate equal to 0 because these are x-intercepts. And this is a cleaner way, well, a more consistent way with the way the textbook presents it to give these intercepts. Y-intercepts, set x equal to 0. Okay, that's a little bit easier because we'll only get one value out, provided 0 is in the domain of the function. We'll set x equal to 0 in the f of x function. That is, we'll take f of 0, negative 3, 0 squared plus 5 times 0, plug the zeros in, get 0 out. The y-intercept is 0, 0. So we've got x-intercepts, we've got y-intercepts. They didn't ask us about symmetry on this one. Yeah, I don't think it has any of the symmetries, just eyeballing it. This is not a good example to address symmetries. I don't think it has any of the symmetries we test for. Okay, another one that's a real world problem. The problem with real world problems is the numbers can be messy. If a player in the NBA shoots an underhand foul shot, releasing the ball at a 70-degree angle from a position 3.5 feet above the floor, then the path of the ball can be modeled by the function h of x equals negative 138.6 x squared divided by v squared plus 2.7x plus 3.5, where h is the height of the ball above the floor, x is the forward distance of the ball in front of the foul line, and v is the initial velocity with which the ball is shot in feet per second. Underhand shot, that's why the ball's so low. It's at 3.5 feet because this was an underhand foul shot. Okay, so the 3.5 plays its role right here. The 70 degrees, we don't know anything to deal with angles just yet. Presumably the 70 degrees is taken care of somehow in this function. This is what we're interested in here. Some of these numbers are relevant. The 3.5 is because it appears here. The 70 degrees is not at all relevant to what we need to do. So they've given us a function. Ooh, it's got something we don't know. The V parameter, we don't know that. Part A says, the center of the hoop is 10 feet above the floor and 15 feet in front of the foul line. Determine the initial velocity with which the ball must be shot in order for the ball to go through the hoop. Okay, we've already done this kind of thing, just not with all these words decorating the question. They want the ball to pass through the hoop, which is 10 feet above the floor, that's a height, and 15 feet in front of the foul line, that's an x value. It says x is the forward distance of the ball in front of the foul line. So they've used intentionally that wording in front of the foul line in stating this. So what they want is when x is 15, the height is 10. When x is 15, the height, this right-hand side, equals 15. That's how we'll work that one. Next, they want to write the function for the ball, for the path of the ball using the velocity found in part A. We'll have the velocity from part A. We'll substitute in here. Determine the height of the ball after it's traveled 9 feet in front of the foul line. When x equals 9 feet, what is the height? That'll be easy because we'll have a function by then. Find additional points and graph the path of the basketball. So we're plotting points and trying to graph. That'll be messy. We'll have better ways of dealing with these soon. But let's answer the questions they asked. First, they wanted to pass through the hoop. So when x equals 15, they want the height to be 10. So we'll plug 10 in for x and set the resulting height equal to 15. We'll plug 10 in for x and set the resulting height equal to 10. I say that correctly, plug 15 in for x and set the height equal to 10. We want it to pass through the point x comma h equals 15 comma 10. X is 15, height is 10. So x equals 15, h equals 10, produces. The height is 10. We'll plug x equals 15 in right there and right there. Producing 10 equals negative 136, 15 squared over v squared plus 2.7 times 15 in parentheses is where I plug the x's in. plus 3.5. Okay, it's a real world application, so that means the numbers are going to probably be a little bit messy. Simplifying a little bit, 15 squared times 136, I guess is 30,600. 2.7 times 15, I guess is 40.5. Certainly would rely on a calculator for this stuff. Let's see, we can combine these two. That's 44, produces a 44. Let's subtract 10 from both sides. Notice this reads 10 equals this quantity here. Subtract 10 from both sides or move the 10 to the other side. Take this negative term, put it on the right-hand side. That produces 30,600 over v squared positive. We moved it to the other side of the equation. Equals 44 minus 10. We brought the 10 to the right-hand side. 44 minus 10 is 34. So there's something quite manageable. So it's just manipulations. We're trying to solve for v. That's the question. What's the velocity? So we're left with 30,600 over v squared equals 34. We could cross multiply by v squared, divide by 34. Convince yourself that all this algebra actually is correct. Pause the video and check it. I've skipped a few subtle steps, but this produces v squared is 30,600 divided by 34, and that's 900. If v squared equals 900, then v is plus or minus the square root of 900. It's plus or minus 30. So I'm sure they engineered this. This is the reason they made it some underhand shot. They've engineered it to get a clean number out for v. But we saw plenty of messy numbers along the way. Presumably, the velocity is positive. So we'll take the velocity to be 30 feet per second. I'm basing that presumption on physics and the fact that this is a problem not just with symbols, and true, v equals negative 30 also satisfies this equation. I mean, it's going to get sucked up. Any negative sign we introduce gets sucked up from the fact that v is squared. So we'll take v equals 30 feet per second, and that will make sense physically. So part A, there's the velocity. By the way, the units were feet per second. I'll keep up with units as I probably should in a physicsy problem. Secondly, part B, they wanted us to write the function for the path of the ball using the velocity, 30 feet per second. Okay, we'll just plug v equals 30 feet per second in right there. V squared is 900, feet squared per second squared. Substituting in that 30 for v, producing a v squared. This is v squared, right? V squared of 30 squared back to 900. And we can simplify that a little bit. What is it? 4 divides 136 and 900. What's 4 times 34? It's 120 and 16. Yeah, that's 136. 4 times 225 is 800 plus another 100. Right. So we factored 4 out of each of these to simplify things, just to make it less bulky. So here's the height as a function of x. If the ball passes through the goal, then v had to be 30. And that produces this. What's the units here? It's height. Height's measured in feet. So this output would be in feet. It wouldn't be a bad idea to write feet out right there. Part C, determine the height of the ball after it's traveled 9 feet in front of the foul line. X measured distance in front of the foul line, so we'll plug x equals 9 into this function. For the next one, we got the function from part B. Moving on. Question is, h of x is what when x is 9 feet? Simply plug the 9 in for x, there and there. So there we go. We saw on the previous slide that the velocity, that the height had simplified down to this quantity, 34 over 225, after the division by 4 thing. Do the arithmetic on this and you get something like 15.56 feet. So it's pretty up in the air, it seems. Part D, find additional points and graph the path of the basketball. All right. Plotting points is not a good way to graph something. Right now, we got nothing else. So how about we plot for x between 0 and 15 output values. So plug in 0, we get 3.5, somewhere around here. It's when the ball was released. Remember, it's an underhand shot. It goes up somewhere around 9. We had the value of 15.56 from the previous, it's somewhere around here. And then it goes down and it goes through the basket. This was the 15 feet over, 10 feet up point, right? The center of the basket's right there. I have plotted these points by hand, as you will do, and tried to join them together with a reasonable curve, as you will do. And it's a little bumpy and lumpy. You have a precise graph of this. I do this in software, and you'll get a nice smooth curve. And probably you can guess when it reached its highest point, what the highest point is, if you graph it with software. But we don't do these by hand, and you learn a little bit more. You also get a little bit more frustrated because it's tedious to deal with a calculator and these numbers and plotting them. And I haven't plotted all 15 of them. Looks like I plotted roughly half of them. But we get behavior something like this. So it makes physical sense. The release point was 3.5 feet. It reached a maximum a little bit bigger than 15 feet. And then it dropped 5 feet down and passed through the basket. And, you know, it'll continue on uninterrupted. Doesn't touch the net, say, not even net. And then it'll follow a nice symmetric trajectory as it comes back down. But plotting points produces this kind of thing. And that's what we get from this problem in terms of plotting points and trying to graph the thing. There's got to be a better way. Let's look at one where they give us the graph and we're going to analyze the shape of this graph. Number 38 says, let C be the function whose graph is given. This graph represents the cost, C, of manufacturing Q computers in a day. So Q is going to be the variable. It's going to be a C of Q function. Cost of producing this quantity. I suspect is why they've chosen Q for the variable. Based on the graph, determine C of 0, interpret the value. Determine C of 10, interpret the value. Determine C of 50, interpret the value. What's the domain of C? What does this domain imply in terms of daily production? Describe the shape of the graph. The point 30, 32,000. Right here is called an inflection point, something you'll discuss in calculus. Describe the behavior of the graph around the inflection point. Okay, so we'll probably have to come back and look at this graph, and I think we're going to stuck in the slides in the future. Determine C of 0. Well, we'll get the point 0, C of 0 as a point on the graph. The point 0, 5,000 is a point on the graph. If this is a function, then that 5,000 must be C of 0. Just read it off the graph. 10, plug in 10, get out, looks like 19,000. Plug in 50, get out 51,000. There's those values from the graph. Spelling it out. The point 0, 5,000 is on the graph, so C of 0 is 5,000. Interpret that. That means if no computers are produced, if 0 computers are produced or manufactured, then the cost is $5,000. To put it in business terminology, this is called a fixed cost. Represents the cost of having employees, keeping a factory open, paying the bills, and so forth. Fixed costs. Even when you don't produce anything, you still incur this fixed costs. 10, plug in 10, we see the point 10, 19,000 was one of the dots on that curve. So it must be that C of 10 is 19,000. This means if 10 computers are manufactured, then the cost is $19,000. The cost was measured in dollars. 50. The point 50, 51,000 was on the graph of C. So when we plug 50 in, we get 51,000 out. That means the cost of making 50 computers is $51,000. And they didn't talk anything about how much you sell them for, what the revenue was and what the profit was. So this is all about the cost function. What's the domain of C? What does this domain imply in terms of daily production? Okay, I need to go back and look at the curve. So let me jump back to the curve. Domain, what can the X values be? The curve starts at 0. Well, that makes sense. It's a quantity. And it ends here, it looks like. It ends with Q equals, X equals, you might think, 100. So the domain is anything between 0, including 0, because there's a point here, up to 100. The curve ends there. They stopped drawing. They didn't put the little arrowhead. So it stops here, starts here, 0 to 100. That's the domain. So back to the question asked. What's the domain? The domain of C is a set of all X values, Q values, for which C is defined. We see from the values on the Q axis that C is defined for Q between 0 and 100, or in interval notation, 0 to 100, square brackets, include the endpoints. The point 0, comma, something or other was on the curve, as was 100, comma, something or other. So the endpoints are included. So daily production can be as little as 0 computers, but it can exceed 100. The function stopped at 100. So for some reason, they can't produce more than 100 computers. That's reflected in the graph. Describe the shape of the graph. Okay, let's actually go back and look at the graph. There's some points labeled on the graph. So cost goes up, up. Then it seems to go up kind of sharply here. And then it goes up precipitously. So the more you make, the more it costs. But at a certain point, the rate at which costs increase per unit production seems to itself increase. So we've got some sort of change right here. They called it a point of inflection, this point 30,000, 32,000. Things change there. You make more and they cost more per unit to make after this point. That is when you make more than 30 of them. So let's try to verbalize that. That's what they wanted. Describe the shape of the graph. The graph increases slowly up to Q equals 30. Then it starts to increase more rapidly at that point of inflection. It starts to increase very rapidly if we go beyond 50. So we interpret this as the cost increases rapidly when the manufacturer produces computers at a level of 50 or more. It increased a bit when we went past 30. So if you wanted to minimize cost per unit, probably around 30 is where that will be. We haven't addressed that specifically, so I should be careful on that. But we could look at cost per unit, and I suspect 30 would play a prominent role in that kind of discussion. Then they wanted us to talk about that point 30, 32,000. It's called an inflection point. Describe the behavior of the graph around that inflection point. Yeah, we just did. This is where the rate of increase grows from growing slowly to growing rapidly. And it changes from slowly increasing to quickly increasing. And then it gets really quickly increasing. But it's right there that it changes. The way you'll deal with this in calculus, and you'll deal with it quantitatively in calculus, is see how the curve, it's going uphill, but it's arching downward. At some point, we'll call this concave down. And then right there, it switches. It's still going uphill, but now it's arching upward. We'll call that concave upward. It's changed from concave down to concave up, and it changed right there. That's what a point of inflection is. In the business world, in economics, this is called a point of diminishing returns. It becomes, the more you produce, more expensive than it had previously been. So point of diminishing returns in a cost function is what economists call a point of inflection, the math term. Math term is point of inflection, point of diminishing returns is an economic expression. And that takes care of section 10.2, introduction to the graph of a function. So what we'll do next in 10.3, right about the next 3 sections, is we'll elaborate on this. Really the punchline in this section was A point on the graph allows you to determine a function value. And conversely, a function value allows you to determine a point on the graph. We need a little more sophisticated approach to graphing than just that, because we ain't going to graph just by plotting points. We will graph and probably plot points, but there won't be just any points. There'll be special points, and we'll know why they're special. We'll have partial success in Precalculus 1. In Precalculus 2, you'll graph trig functions. Actually be pretty good at graphing trig functions. You'll be good at finding special points algebraically, trigonometrically. But it won't be till you've had Calculus 1 that you have all the equipment you need to graph. But we'll do what we can, and we'll be pretty successful. But you'll learn a lot more about graphing in Calculus 1. One of the main applications of Calculus 1 is to graphing. So I'll see you in the next section, 2.3 shortly. Have a nice day. Catch you later.